Now, in order to study the high frequency response of the CS amplifier, that is the common source amplifier, we need to augment the high frequency model into the common source small signal equivalent circuit. So let's draw this. Here we are. This is the circuit that we wanted. However, notice that this is quite complicated, especially in the middle region between gate and drain. You have a capacitance CGD, which complicates our calculations. Fortunately, we can simplify this circuit via two methods. We can use the Thevenin theorem at the input side, and we can also combine the three parallel resistances at the output side, like this. Now our circuit is much more simplified. Now let's start our analysis by first writing an equation for the current through the load. Remember what we are trying to find? Our aim is to find an expression for FH. Now, at very high frequencies, it is reasonable to assume that IGD is much smaller than GMVGS. So, IRL dash is approximately equal to minus GMVGS. Now using that, we can write the equation for V0 minus GM RL dash VGS. We can write an equation for IGD, however, VGS minus V0 divided by 1 over S CGD. This is the reactance of the capacitance. Rearranging, we get IGD equals S CGD, brackets open 1 plus GM RL dash, brackets close, VGS. Now there is another way of further simplifying the circuit. Take a look at this line X dash. The left hand side of the circuit at X dash knows of the existence of CGD only through the current IGD, correct? Therefore, we can replace CGD by an equivalent capacitance C equivalent between the gate and ground as long as C equivalent draws a current equal to IGD. Let me write this expression on your top right. This can further be simplified. Now let me draw this on the circuit, correct? We have also introduced a new quantity Cin, which is simply the sum of the capacitances CGS and C equivalent. Remember that when capacitances are connected in parallel, the effective capacitance, which is found by shorting this first, is simply the sum of the two capacitances connected in parallel. So Cin is basically C equivalent plus CGS. Now this separation of the two parts of the circuit simplifies our circuit even more. This circuit is also a single time constant low pass type. For full details, please see the link in the instructor's notes. These circuits are easy to use and we can express their output voltage readily. For the left hand side, we can write this equation of VGS on your screen. Notice this new quantity omega naught. This is the corner frequency or the break frequency or the 3 dB frequency of the circuit to the left. And omega naught is given by this expression 1 over Cin R sig dash. So this is pretty textbook stuff. Now to link the right side with the left side, we put this value of VGS back into the equation of V0, which was the first one that we derived. And we get this expression. Now notice that the numerator is basically AM. So we can write this equation as AM divided by 1 plus S over omega H. Now omega H is obviously equal to omega naught. And so we have found the frequency that we were looking for. Converting omega H into FH is pretty straightforward. And we get FH as 1 over 2 pi Cin R sig dash. Now notice the right side of the circuit is not a single time constant low pass or high pass type. It is simply a parallel combination of a voltage controlled current source and an effective resistance lumped together. The time constant arises in that part of the circuit which has capacitances. So basically what we did was that we isolated that part of the circuit that had capacitances and we calculated its output expression via the standards given to us. Then using those standards we found the value of omega h. Now remember, our purpose in finding fh was to see how many physical quantities we can manipulate to bring about the desired value of fh. Now first of all, look at this expression. In it we see two parts, Cin and R sig dash. In R sig dash, the things that we can manipulate are Rg and R sig. In Cin, the things that we can manipulate are Gm and RL dash. CGS and CGD are fixed for the MOSFET. And of course in RL dash we can manipulate RL and RD. This is basically what we mean when we say design. We have to choose appropriate values for all of these things so that fh can be as desired. Now let's discuss one more thing. The multiplication effect that CGD undergoes here comes about because it is connected between two nodes whose voltages are related by a large negative gain minus GMRL dash. Look at the top diagram. I have written the two voltages V0 and VGS. And if you remember the relation, it was minus GMRL dash. Now this effect is known as the Miller effect. And 1 plus GMRL dash is known as the Miller multiplier. It is because of the Miller effect that the value of Cin was so high, because as you know, CGS and CGD are quite small capacitances. And because of a high Cin, we have a low FH. So it is better to have situations in which the Miller effect is absent or reduced significantly. We are going to look at this in the next course. In the next course, we are going to dispense off some liberties we had taken in this lesson, namely neglecting IGD when calculating V0. In the next course, we are not going to do that and carry out a more precise analysis, but for the purpose of our discussion here, this is more than sufficient. And now we move on to the low frequency response.